Hi everybody, this is lecture 22 and today I'd like to continue telling you about surface integrals. So I already drew for you a surface and a parametrization of a surface, right? So this gives me a description of points on the surface which have x, y, and z coordinates in terms of just two numbers, and the fact that two numbers suffice to describe points on the surface is reflected in the dimension of the surface. It's a two-dimensional object, so you need two coordinates to locate points in that object. Okay, so we have a parametrization of the surface, and this is going to be necessary for whenever we do a surface integral. We're going to need a parametrization. So here, that's why I set the stage like this. Let's look at an integral like we defined last time. So last time we defined integrals of functions over surfaces. So I should note that later we'll talk about integrals of vector fields over surfaces. So flux across a surface, for example. But for now, today I want to focus on just integrals of functions. So I said that these are defined by Riemann sums, like other integrals of functions we've seen before. Okay, defined by Riemann sums, or limit, I should say. This integral is a limit of Riemann sums. In the game, so we have a function and a surface, and what we do is, so you take a limit of Riemann sums. One particular Riemann sum you get by breaking, the surface into a bunch of little pieces, and then for each little piece you pick a point inside it, and you evaluate the value of the function at that point. You evaluate the function at that point and multiply by the area of the little piece. So you get a number that looks like this, except you get delta s for the area of that little piece instead of ds for the infinitesimal version of that. And then you add over all little pieces. And this integral has the same applications as before. So for example, the same applications as before. So as before, I mean as other integrals of functions. As other integrals of functions. For example, if I integrate the function 1, if here I have the constant 1 and I integrate, I'm just breaking up the surface into a bunch of little pieces, adding the area of each little piece, multiplied by 1, that's just the area of each little piece, and so the result is the area of the whole thing. So if I integrate 1 times ds, I get the area of the surface. If instead I integrate some density, for example, the amount of mass per unit area on the surface, if I multiply mass per unit area with the area of a little piece, you get the mass of a little piece. Add over the whole surface, you get the mass of the whole surface. Or if you integrate the distance from an axis squared and then multiplied by the density, if you integrate that, you get the moment of inertia about that axis. So you get all those applications. Here I'll just so for example, the double integral. So the most general sort of interpretation is this for the integral, that if you integrate a function over a surface, the result is the area of the surface multiplied by the average of the function on the surface. So this is if I can write, here there's only space for one application, and because this is the most fundamental one, right? So this, if I had to choose one, this is the one I choose. But I just wanted to note that these integrals have the same applications as before. All right, so this is what they're good for. Here's how we compute these numbers. So we compute the integral using a parametrization. So instead of doing directly an integral over S, I'm going to use this parametrization, which is a dictionary between points in D and points in S that maps points in D to points in S. Right, so I'll do a double integral over D instead, and then I will evaluate my function at, so this double integral, so here I have to evaluate a function of points in D, so this is the point. So if you give me u and v, r of uv is the corresponding point of the surface, I evaluate the function at that point. And then I'll multiply the function, so instead of using du dv, that's area in the UV plane, I'll use the area of the corresponding region of the surface, right? So this is ds, and this is du dv, right? So ds is ds has not the same area as the little square rectangle. It's actually, so the scaling factor is the length of the cross product of the two partials of the function r multiplied by du times dv. Okay, so this last piece is ds. So like the infinitesimals, du and dv, they don't make sense by themselves. They make sense only when they're part of an integral. But I'm saying that whenever you see ds in an integral, you will substitute that by this multiplied by du dv, given this parametrization. Okay. So this is how we compute these integrals. So I'd like to make a couple of remarks next. I'd like to compute these cross products and see what ds looks like, and I would like to compute these in a couple of examples. First, I'll start with more theoretical examples that relate these integrals to things that we've seen before. So, for example, you guys must be wondering about the relationship between this and change of variables in double integrals, right? There we had a very similar thing. I was integrating, so there was no z. I was integrating f of xy over a flat region of the xy plane, and then I changed that. I reinterpret that function. I rewrote that. We could compute that integral by rewriting the function in terms of new variables u and v, but then instead of I would replace dx dy by some Jacobian determinant, the absolute value of a Jacobian determinant times du dv. So there is a lot of similarity here, and that's not a coincidence. In fact, that sort of change of variables is an example of this. So I'd like to show you that, and also I would like to do a calculation once and for all that's going to be useful all the time. So the special case where the surface is a graph, I'd like to show you what ds looks like in that case, and then we'll recover the formula for the area of a graph that we've seen before. Okay, so these are and lastly, after doing these two things, I'd like to show you I'd like to do a more involved computation of a double integral over surface. Okay, so let's do all these three things. So example number one, here let's start with the graph situation. So S is the graph of a function. Okay, the graph z equals f of xy over a region D of the 2D plane. So here's how we parameterize a graph. We've talked about this. So if I want to know a point on my graph, I can just describe, if I know the x and y coordinates and I know what graph I'm talking about, I also know the z coordinates, just given here in this equation. Okay, this equal sign is kind of conflicting with the other one. Let me just replace that by saying S is the surface with these two, described after the colons. Okay, so R of x and y, the parameterization is x, y, f of x, y. And then, so what's ds? ds is the length of the cross product of the two partials. So here are two partials. So that's, so So this is a determinant. Let me bring this one line down. So cross product is a determinant where the first row is the three standard directions. In the second row, you put the first vector, that's the x partial, that's 1, 0, and then the x partial of f. And then the second row is the third row is the second vector, that's so the y partial of 0 of x is 0, y partial of y is 1, the y partial of f is f sub y. So if I compute this, I get I get I times, so the first component is, that's the thing multiplying I, is 0 minus f sub x. And then the j component, so then you get plus j, so the j component is the determinant, this determinant done backwards, so just get minus f sub y. And then the k component is 1 minus 0, that's 1. Okay, so we get that ds is the length of r sub x cross r sub y times dx dy. Well, this length over here in this case is something we've seen, right? It's the square, so it's the square root of the first component squared. The minus sign goes away when you square a real number, any number in fact. So it could be complex as well, but here we're not working with complex numbers. So we get this, I said the minus sign goes away, but I didn't really take it away. Anyway, you get these three numbers squared inside a square root, and that's that. So for example, so we recover the fact that the area of the surface is the double integral over the region of the area of this graph is the double integral over the projection over the region where the function is defined. So the projection of the graph, and then you multiply the function 1 times ds. Let me just write that in 2 stages. So it's integral of 1 times ds. That's the area. That's true for any surface, but for a graph, we can use the parameterization I wrote here, and then you get that's the square root of f sub x squared plus f sub y squared plus 1 times dx dy, right? Just because this last part is ds. So you see this new formula that we have, we can use this new integral to compute areas, and we get everything that we knew, all the areas we knew how to compute before. So before we knew how to compute areas of graphs, but we get more, right? We can describe surfaces we can compute the area of surfaces which are not graphs. For example, the sphere from last time. The sphere is not a graph because it fails the vertical line test. Right? If you fix x and y, then there are two z variables, 2z values on that surface with those x and y values. All right. So the other example I'd like to show you, how this integral connects to how this expression for the integral in terms of parameterization, how this connects to change of variables before. So example. So S this time is flat and on the xy plane. Okay, so here is, so let me draw that. So instead of having our surface, fly, be up here and be like, it's going to be flat and it's going to live in the xy plane. So I'm going to get something like this. So that's our surface. And so in this situation, r of x and y is so it's x in terms of u and v. Oh, not r of x and y. So I'm sorry. We have a parameterization of the surface. So we're describing points on the surface in terms of two numbers u and v, and then You get x in terms of those numbers, y in terms of those numbers. And then you get z in terms of those numbers. But it turns out that on this surface, z is always 0. On a flat surface inside the xy plane, that is on a region of the xy plane, z is always 0. So this is our parameterization. This is the most general parameterization of a region of a flat surface in the xy plane, that is, of a region of the xy plane. Okay, so in this situation, let me bring the parameterization with me to the other side. So with this parameterization, the length of the cross product, so first let's look at the cross product and then ask about its length. So the cross product is going to be this. We're looking at a pretty general parameterization. So here we put, so the u partial of x, that's dx du, and then the u partial of y, that's dy du, the u partial of 0, that's 0, and then the v partial of, my apologies, it's not r sub y, it's r sub v. Then we do the v partial of x and the v partial of y, and then the v partial of 0, that gives me 0. So if I compute this, you see that I gets multiplied by 0, j gets multiplied by 0, k, though, gets multiplied by this. So this cross product just becomes just points up, right? You get dx du times dy dv minus dx dv times dy du multiplied by k, right? And here you recognize the Jacobian determinant. So that the thing we've been writing, we've been calling dxy over duv. We were talking about the change of variables, right? So when we talk about the length of this vector, it's just the absolute value of this function. Well, the k has just length 1, k hat has length 1, so the length of this guy is just the absolute value of this function. That is the absolute value of the Jacobian determinant. So you see, if I integrate, so in this situation, so if S is a flat region in the xy plane, then the integral of so z would be 0 always. I would have a function of so I'm just looking at what this function looks like in the xy plane. I can just set z equal to 0. I'm left with the function of the first two variables. So I'm just plugging plugging the formulas for x and y in terms of u and v in terms of inside f. So this is the first step, and second step is multiplied by the absolute value of the Jacobian determinant. Of this cross product, but that's the absolute value of the Jacobian determinant. Okay. So one thing I'd like to note is that we've seen this cross product and also this cross product before. So here, we said, okay, so we have a parameterization and it depends on two parameters. But what happens when you take a partial? Well, you're fixing one of the parameters and then letting the other vary and differentiating, right? So if I fix v and let u vary, then I have only one free parameter that draws out a curve on my surface and inside my surface. And if I take the partial, I get the velocity vector of that curve, which is tangent to the surface. This other partial is the same. It's another velocity vector of a different curve on the surface. So once I have these two and I take a cross product, I get something that's tangent, that's perpendicular to 2. The cross product is perpendicular to 2 independent vectors on the surface, right? So we have these two independent vectors on the surface, and then the cross product is perpendicular to both, so it's actually perpendicular to the surface. So this, so this cross product is normal to the surface. That's what we've seen in the past, and I try to recall very briefly now. And you can see that this is indeed the case in this example. The cross product is a multiple of k, right? K points up, so k is normal to the surface. And also this cross product here, which is the Jacobian determinant times k, is well, it's absolutely normal to the surface in this example. Okay, so with all these remarks out of the way, let me show you now. So let me wrap up today's lecture with a nice example of a real-life example of an integral. Our job is to compute the double integral over a surface S of the function z with respect to ds. Okay, and the surface is going to be a lipstick shape. So I'm going to draw, today I'm going to draw, so here I'm going to draw the axes in a funny way. Let me just move this down. Yeah, let me just move this here. So the axes are here. And so this is x, this is y, and sorry, this is z, and I have to satisfy the right-hand rule. So if I go from x towards the y-axis, with the fingers in my right hand, I should my thumb should be pointing up, and this happens here. Right. So here is my hand, and here's my thumb. Okay. So this is the axes drawn in from a funny angle. Let me now give you the surface. So it's going to look like this. It's going to have three parts. Okay, so we have our surface. So it has three parts. There is one part you can see here, that's the side. So I'll call it S1. So this is a cylinder over the circle of radius 1. Okay. It has another, so this surface has another part, that's the bottom part. So this is S2, and it just has equation z equal to 0. And the last part is this top. So this is an ellipse, the interior of an ellipse living inside the plane. So this is S3, which lives inside the plane z equals 1 plus x. Okay, so we have this. We have equations for all of the sides, all three sides, and then we know what this picture looks like. So let me note, for example, when x is 0, then z is 1. When x is -1, so on this left part on this point here in the circle, z is, if x is -1, then z is 0. So you see that this ellipse does indeed touch the circle at the bottom at this point. And right, if you want to know this height over here, that's if x is 1, then z is going to be 2. Okay, so this is, we have a clear, I think we have a clear understanding of this picture. I'm going to need that line in a moment, so I'm going to move this down. All right, so our job is to compute this double integral over the surface. So this is going to be a little bit of work. We have to do three integrals really: one on S3, one on S2, and one on S1. Right. So S is the union of all three. So let's look at S1 first. Let's start with the heavy lifting. So this is the side of our the side of our shape, of our surface. So this is a cylinder, right? S1 is a part of a cylinder. And so we have to parameterize S1. So here's a general strategy. So S1 is a part of a cylinder. So if I just had to parameterize points on this, if I had to parameterize the whole cylinder, I think the natural variables to use would be theta, which tell me the angle around the z-axis, and then z, the height. You know, the z is just the last coordinate. So if I know theta and I know z, then I know a point, right? So for example, here, this is theta and this is z. I can get any point on a cylinder. So if I know theta and z and I know the radius of the cylinder here, it's 1, I can find points on the cylinder. So I'm going to use this parameter. So here we have a part of a cylinder, and the way to parameterize that is you just use the same, well, this is a strategy that works quite often, is so you use the same parameterization that you would use for the whole cylinder, but then you restrict the parameters to just cover the part of it that you care about. So here, let's do that. Let's use theta and z for our parameters. And so, so x in terms of theta and z, so theta is the angle around the z-axis, so x is just, you know, the radius 1 times cosine theta. Y is the radius times sine theta, and z is itself. But now we have to constrain theta and z to just describe the part of the cylinder, the side of the lipstick shape that we care about. So here we need all angles around the z-axis, right here. For example, just to cover the points on the bottom, I need all possible angles. So theta goes from 0 to 2 pi. And but z is not at all constrained, right? For example, for this value, well, for theta equal to 0, z ranges from 0 to 2, right? For theta equal to pi, on the other hand, z ranges from 0 to, well, from 0 to 0. Z doesn't vary at all. Z is constrained to be that point for theta equal to pi. So on average, in general, z goes from the range for z depends on the value of theta, right? And in general, z starts at 0 and stops when it reaches this plane. So it stops at 1 plus the x value for that value of theta. So z stops at 1 plus, stops on the plane at 1 plus x. But here, x in terms of theta is 1 plus cosine theta. So let me remind you that when we have a parameterization, the first, second, and third components are x, y, and z. Okay, so these are our bounds for the parameters. This describes the side of the lipstick. Now let's compute the cross product of the partials. So because we want to do an integral, we have to compute these partials. So here's I. Here's j, here's k. So first, dx d theta, that's minus sine theta. dy d theta is cosine theta. dz d theta is 0. Now moving on to this other line, to the z partials, dx dz is 0, dy dz is 0, and dz dz is 1. So as a result, when you compute this determinant, I get I times cosine theta. So the first component is cosine theta. Then I get j times 0 minus sine. So that's theta, that's just sine theta. And finally, the k component is 0 minus 0, that's 0. Okay, so here's an interesting observation. This normal, it doesn't have a z component. So this cross product, this is an observation that's going to be very useful for us later, but not really necessary to proceed with the computation. But please bear with me for a second. Let's just note that this cross product, the z coordinate is 0. I told you that this is the normal to the surface. So the normal has z coordinate 0. This is consistent with the picture we see here, right? If I give you a point, like this, the normal is pointing out of the surface like that, right? So r sub theta cross r sub z, and it's really so the x and y coordinates are just the x and y are. So this is x. This point is x is cosine comma sine comma z, and this normal is cosine comma sine comma 0. So it's just a copy of this vector but placed over here, and so that it really looks the way it should. It's really the normal you expect. Okay, so we have the cross product, so we can compute, well, the length in this example is just easy. It's going to be a nice, it's just a constant, right? It's the square root of cosine squared plus sine squared plus 0 squared. That's the square root of 1, which is 1. Okay, so our integral over the side of the function z times ds is just, so the double integral. So now we're doing a double integral in the theta z plane. So theta goes from 0 to 2 pi. Z goes from 0 to 1 plus cosine theta. And then we're integrating the function z. Here I've written z in terms of the parameters, theta and z, so z is just itself. I'm using it as one of the parameters. And then I'll multiply that by the length of the cross product times dz d theta. And we just noted that this part is 1. So at this point we're happy, right? At this point we're just left with an ordinary iterated integral that we can compute. So theta goes from 0 to 2 pi, and then we're integrating z with respect to dz. That's z squared over 2, evaluated between 0 and d theta at these 2 points. So, sorry, at 1 plus cosine theta at the top. So this is the integral from 0 to 2 pi of 1 plus cosine theta squared over 2d theta. And I think here I may want to cheat and look at my notes. Yeah, I do. So in the notes, I told myself the result of this integral is 3 pi over 2. So that's the integral over the first part of the surface. So the side of it. Okay, so this integral is going to be 3 pi over 2 plus the integrals over the other 2 sides. All right, it turns out that the integral over S2 is going to be pretty fast. So over S2, so the double integral over S2 of z times ds is just, well, this is an easy one. It's just the double integral over S2. So on S2, the function z, so S2 is the bottom, right? So on S2, the function z is always equal to 0. So the integral of 0 over this disk is of course, it's going to be 0. Right, so that's nice. That's a nice one, but we still have to figure out the integral over S3. Let me just say, so let me just say that if I wanted to parameterize this disk, I would just say that I would use, because it's a disk, I would use r and theta, polar coordinates, and say that x is r cosine theta, y is r sine theta, z is 0 on this disk. And then I would compute if I wanted, I would have to compute the length of the cross product times dr d theta. I mean, that's not going to matter because it's going to be multiplied by 0 when you do the integral when you set up this integral. So that's why, I mean, if you integrate the function 0 over any surface, in particular over the disk, you're definitely getting 0. This sounds obvious, and if you, with a little bit of work, you do get to reach that conclusion completely rigorously. Okay, let's look now at the third side. So the third side, we already did some of the work. So S3 is the top, right? So S3 is this, and we're looking, so S3 is really an example that we've already looked at, right? This is Z equals a function of X and Y, right? 1 plus X is definitely a function of X and Y. So here, so S3 is really a graph over the unit disk, right? The region, this disk here, it's inside the cylinder of radius 1 around the Z-axis. So we're really looking at the function 1 plus the graph of the function 1 plus X over the unit disk. So let's just work with that. So R. So here we have graph. So R, we can describe points in this graph using X and Y. This is f of x, y. And then we've seen that the cross product r sub x cross r sub y is minus the x partial of the function minus the y partial of the function and 1. So if I work this, so in the present case, the x partial is just 1, the y partial is 0, and 1 is just itself. And so the length is root 2. So let's set up this double integral. So the double integral over S of Z times ds, sorry, over S3, the top, is, so x and y here, they belong to the D, the unit disk, about 0. Right, so that's actually part, so this description, this constraint on the position, so this range for x and y is part of the parameterization of the surface, right? So if I didn't say this parameterization would be of the graph of a whole plane rather than in an ellipse on the plane we're talking about. Okay, so here let's do the double integral over D. Over this unit disk, and then Z is the function 1 plus x, all right, and then we multiply, so Z in terms of x and y is just 1 plus x, okay, we multiply that by the length of the square root of this cross product times dx dy, right? The x and y are the two parameters, so the length of the cross product in this case is just root 2, right, because here's the cross product. And now this is a double integral for me to evaluate. And if you think about it, we want to change variables. We want to use r and theta. So let's do that. So let's change to do this, to compute this double integral over a disk. Let's change to polar coordinates. So theta goes from 0 to 2 pi. R goes from 0 to 1 because it's the unit disk. Then we're integrating 1 plus r cosine theta. I almost did something wrong there. So we're dealing with three things in succession. And a while ago, x was cosine theta, but that's no longer the case. At this point, x is r cosine theta. I'm changing. So here I have a double integral, and I'm just changing variables in that double integral. So when you introduce polar coordinates in the double integral, x is r cosine theta, and y is r sine theta. They're not cosine and sine as they were here, and they're not. They're not themselves as they're here. Here we're changing to polars. Okay, so multiply by root 2 and then r dr d theta. And so this gives us root 2 times the integral for theta from 0 to pi, and then the integral inside, the integral of r is just r squared over 2, plus the integral of r squared, that's r cubed over 3 cosine theta d theta. That's just root 2 times, my apologies, I have to evaluate the integral between 0 and 1. So this integral, this integral inside, this evaluates to 1/2 plus 1/3 cosine theta. And now the integral, so this just gives me root 2 times the integral of 1/2 from 0 to 2 pi, that's 1/2 times 2 pi, plus the integral of 1/3 cosine theta from 0 to 2 pi, and that's 0, because the integral is the signed area between the graph and the theta axis in this case, and cosine on a full period stays the same amount of time above the x-axis, above the theta axis as it does below. So here, the integral of cosine is just 0. So result, pi times root 2. So this is the integral of z over the top piece. So this is the last part, is pi times root 2. Okay, so thank you so much for listening, and I will see you guys next time.